Kia ora and welcome to video 5 in the series Insightful Integration. In this problem, we're finding an area, or in this case, two areas. I've given you the hint with the graph there that some of the area is below and some of the area is above. There was a past scholarship question 3 years ago, maybe, where the region the curve did actually cross the x-axis within the interval you were asked to integrate. And I imagine many students didn't even check that and just integrated between, in this case, 0 and pi over 3. So don't integrate between 0 and pi over 3 for this problem because you'll get it wrong. The other thing is the curve itself has a pretty ugly looking equation there. So you're going to have to simplify that expression before you begin. All the best with the problem, and we'll catch you after the music for the solution.
Alrighty, the first thing we need to do for this problem is derive a trig identity to integrate this beast. We need to integrate it between 0 and pi over 6, and the answer to that will be a negative number. We take the absolute value for the area, and then we also need to integrate the same expression between pi over 6 and pi over 3. We need to do that separately, otherwise the areas will cancel each other out. So it always helps to draw a graph of the function if you're not given one. But yeah, to integrate this expression, we need to find the integral between 0 and pi over 6 of y with respect to x, absolute value, plus the integral between pi over 6, like I was saying, and pi over 3. The expression there for y is an absolute mess, and I don't think any nice integral substitution would help. So let's look at a trig identity. It makes sense to look at the compound angle formula for tan. So tan 3x, it's quite a common proof here. Use the compound angle formula and you split 3x into x plus 2x. In fact, I think one of my trig videos I released earlier this year looks into this. So we've got tan x plus tan 2x all over 1 minus tan x tan 2x. And then we can use the double angle formula or the compound formula again on the 2x's. So that's going to be that. And then in the bottom, the same thing. So replacing the tan 2x's. And then to tidy this expression up, we can times the top and bottom of the big fraction by 1 minus tan squared x. So if I do that, I get tan x multiplied by 1 minus tan squared x. I'm getting rid of those denominators there by timesing everything in the top and everything in the bottom by that denominator. So I get just a 2 tan x there. And then in the denominator, 1 minus tan squared x for the one part, minus 2 tan squared x for the other part. And then tidy it up a little bit. We've got 3 tan x in the numerator. And you know you're on the right track because it looks very similar to the expression that we were hoping to integrate. So that is tan 3x. Okay, now I'm just going to take that and bring it up here and have a look at how it compares to the thing we're trying to integrate. We are trying to integrate the expression y, which is tan cubed minus 3 tan. So it's the negative of, and the tan 3x, this bit's on the bottom. So we need to play switcheroos with the stuff at the bottom of the top, and then we need to take the minus of it. So the expression y is going to be equal to 3 tan squared x minus 1. Okay. So we're trying to integrate y dx is the same as the integral of 3 tan squared x minus 1. Okay, now we need to think about how to integrate tan squared. it's not tan cubed over 3. It's not on the formula sheet, but there is an identity that's closely related, and that's sec squared minus tan squared equals 1. And the reason I use this one, if I just rearrange it, tan squared x is equal to sec squared minus 1. The antiderivative of sec squared's on the formula sheet, it's just tan. So if I can replace that stuff, we're integrating 3 lots of that, so 3 sec squared minus 3, and then minus another 1. Okay, and then that is 3 tan x minus 4 x, and then plus c, but we don't need the c for the definite integral. Okay, so then our area, our first area needs to be absolute valued. We've got 3 tan x minus 4x in between 0 and pi over 6. Put the absolute value on that because it's a negative number. And then the second one is 3 tan x, same antiderivative because it's the same expression. But this one here, pi over 6 to pi over 3, we don't need to absolute value it because the antiderivative, substituting in those two numbers, we'll get a positive number out of it. Okay, if I sub in 3 tan pi over 6, the first thing I get 3 over root 3, because tan of pi over 6 is 1 over root 3. Then I get minus 4 lots of pi over 6, which is minus 2 pi over 3. The bottom limit, tan of 0 is 0, so that's it, and that's the absolute value of that. And then the second bit, 3 tan pi over 3. Tan pi over 3 is root 3, so I get 3 tan... Oopsies, no, I don't get 3 tan, I get 3 root 3. And minus 4 lots of pi over 3. And this one I need to evaluate the lower limit. 3 tan pi over 6 appears again. That was 3 over root 3. It doesn't cancel with the 3 over root 3 from earlier because we're taking the absolute value of that expression. And then minus 2 pi over 3 again. Okay, and if we simplify all of that, the answer comes out to be square root 3. I'll leave you to check that.